Both problems 1 and 2 refer to finding the average net force. I told you we'd discuss why it's called average. So let's consider, for example, what happened in problem 1 where the baseball was being hit by the bat. And we can draw some pictures of this. So here is the baseball approaching the bat, and the batter is going to swing and make contact with the ball. So here's the next picture where there's contact just barely being made between bat and ball. And then, of course, the batter is doing what his coach told him to do and swinging through and following through. And if you ever see some high-speed photographs of a baseball being hit by a bat, you can actually see that the baseball deforms. You can see it sort of squishes side to side there. It's being pushed by the bat. And then we continue the swing of the bat, and the baseball is still just barely in contact with the bat. And then after situation, the ball completely leaves the bat and the swing is done. Through this process, the force between the bat and the ball actually changes. So we can plot this out on a graph. Let's say here's going to be a graph of the net force on the ball versus time. Now, I'd say its net force is really just the force from the bat, but so we can see what happens later on, we're going to call it net force. And the force does change. Obviously, in the first picture, before there's any contact between bat and ball, the force must be 0. And the last picture, after the ball completely leaves the bat, the force is once again 0, and in between, the force actually grows and shrinks. And so it turns out the shape of this graph, force versus time, looks something like this. Maybe it's not quite as smooth as this. In fact, in reality, it's usually not. It's usually quite jagged, but we sort of idealize it. It becomes sort of a smooth curve where it starts at 0, ends at 0, it peaks somewhere in the middle. Anytime we deal with a graph, we always want to think, what can we calculate from that graph? And there's usually two things you might want to calculate from a graph. One is slope, and the other is area. So why don't you just pause the video and consider which of those two quantities would get us something useful based on what we're plotting here, slope or area. Well, anytime we're doing this, we want to refer back to equations, right? And so the slope, well, that would be force divided by time, or the units of newtons per second. And we don't have any equation that has force per time or newtons per second as units, so it must not be that. It must be the area. And hopefully you see, if you were to take the area, it would be the product of sigma f times t, and you look up equations, you say, oh, I recognize that. The area then must be the net impulse, which is sigma f times delta t, and net impulse is also equivalent to change momentum. So the area under the curve here would get us either the net impulse or the change momentum throughout this interaction. Now, finding the area is really beyond what we can do here. You actually need calculus to be able to do it, but we can sort of make an approximation. Let's say we imagine that while the force really changes, let's imagine it's a constant force, sort of like an average force, somewhere down the middle. And so here I'm going to bound this area, forming a nice rectangular shape. And we can find the area of a rectangle very easily, right? Just length by width. And so this is sort of an approximation of what's happening here. Finding the area of this rectangle would give us an approximation of the net impulse or the change of momentum experienced by the object. It's not reality, but if you can see that the force starts at 0 and it peaks somewhere here, and we imagine this to be a constant force throughout, it's sort of like an average force. All we have to do is realize that in finding the area of this rectangle, we're including some area that really isn't under the curve here, and some area that isn't under the curve there, and we're excluding this area that really is under the curve, that really should be included in the area. So we want to sort of imagine this average force to be somewhere down the middle, so that if I were to take this area that we've excluded by the rectangle, split it up, and sort of drop it in, you should be able to see that this area is kind of about the amount of this area, and this one is about the amount of area there. And so we just have to sort of take our best guess as to what the average force could be to make an approximation here. And so this is why a lot of the problems refer to finding or using an average force, because it's too complicated to imagine what really happens as the force changes if it's going to change in this sort of manner. Now let's turn in our problem set to problem number 4. Go ahead and read that, and go ahead and get started. Well, look what we have here. We have a graph of net force versus time. It's almost like we just looked at that. Letter A asks us to find the car's change of momentum. How can we do that from a force versus time graph? Well, we just showed that the area underneath a force versus time graph is net impulse or change of momentum. We're just going to be breaking it up into different sections. So for letter A, we're finding the change of momentum. For just the first 3 seconds, we clearly see we have a nice triangular shape. So area is going to be the change of momentum. It's going to be half base height, where the base is going to be the 3 seconds, and the height is the 5 newtons. So nothing fancy here. 1/2 3 seconds times 5 newtons. That's going to get us a change of momentum of positive 7.5 kilogram meters per second. We do want to put a sign on it to indicate direction, and we have a direction implied here with the initial velocity being positive 2.4 meters per second. You might recall on a graph, positive usually means forward and negative usually means backward. So in this case, the change of momentum is forwards in the same direction as the object's motion. This object is gaining 7.5 kilogram meters per second of momentum. Letter B asks us to find the car's final velocity at the 3-second mark. How do we do that? Well, change of momentum, remember, of course, is final minus initial. So rearranging that, final momentum would be initial momentum plus delta p. This is where we had started with the vector diagrams in our previous video. We can calculate the initial momentum from the mass and the velocity given, and we have the change of momentum. So this way we can find the final momentum. From there, we should be able to find the final velocity. Just putting the numbers in here. This would get us the final momentum. How do we find the final velocity from that? Well, Pf equals mvf. So solve for Vf as dividing the final momentum by the mass. And we should be getting positive 3.7 meters per second. Remember, it does ask for velocity, not speed. We need the direction on there. Does this make sense? Well, the problem the object started at 2.4 meters per second and it gained momentum, so we should expect that's moving faster now. Letter C is the change of momentum for the entire 8 seconds. Well, we've already found the area for the first 3 seconds. All that remains is to find the area for the next 1 second, from 3 to 4 seconds, and the area for this chunk of the graph from 4 to 8 seconds. So if you haven't yet, pause the video, do that on your own. So we'll break it down. In letter A, we already found the change of momentum for the first 3 seconds. Now let's look at the chunk of time from 3 to 4 seconds. Again, it's a nice triangle, half base height. We should be getting positive 2.5 kilogram meters per second, where the base is 1 second, because we're going from 3 to 4, and the height is 5 newtons. Our next chunk of time is from 4 to 8 seconds. Now here we, of course, are looking at a triangle, but the forces are negative, and that matters, right? You might recall, it's been a while, but area above the horizontal axis is positive, area below the horizontal axis is negative. So we're looking at this triangle here, where the base is going to be 4 seconds, right? From 4 to 8 seconds, that's the base of 4 seconds. And the height is negative 2.5 newtons, giving an area or a change of momentum of negative 5.0 kilogram meters per second. And then for the total, we're just going to put it all together. In the first 3 seconds, the object gained 7.5, then it gained another 2.5, then it lost 5, and so the net result here is a gain of 5.0 kilogram meters per second. Then for letter D, we're going to follow a similar process, finding the car's final velocity. Go ahead and try it on your own. And you should get a final velocity of positive 3.2 meters per second.